I am here. Hello, Ranty. How do you do? Yes. Mhm. Thank you very much. Well, I do try. I mean, just trying to highlight some of the main points, some of the main
Let me start. Hang
misconceptions.
on, wait a minute. Let me start that again. Because I didn't have any sound, right? So let's start this again. Right, okay, well, nice to see you in here, Spurs. So it was about a week and a half ago when you messaged me with this pressure thing that was going around and around and around, and all of a sudden it was like you're phoning me up, and then we're having a chat about it, and here we are with the presentation. You've spent a lot of time on it, you've worked hard.
Mhm.
I've actually saw it. I saw it. You showed it to me last night, so I downloaded it, ready to play. And
Mhm.
I have to commend you because you've put a lot of work into it. So it's whether or not it's going to stand up to the scrutiny of the audience.
Absolutely. Well, yeah. I
You
mean, that's
know,
what it's. Yeah, that's what it's for. Questions, answers. If there's anything that anything I got wrong, then I'll be glad to correct. But we'll just have to wait and see. So.
indeedy. Well, without further ado, if you want to stick yourself on mute, my friend, and we will get this show on the road. Episode number 11, Under Pressure with Spurskimo, and here we go.
Hi, my name is Jody Gilbertson, and I go to Eagle Middle School. And my weather question is, why is it that high weather pressure is associated with fair winds and clear skies, but low pressure is associated with dark clouds and precipitation?
Great question. So we're talking high pressure and low pressure. She's saying, why is high pressure associated with clear skies and light winds, and low pressure associated with storms and rain? Well, we're going to put it together this way. You have to look at weather as three-dimensional. That's the key here. That was one of the most difficult college. When they started talking about the weather in three dimensions, I was so used to just staring at weather maps that I'd see in the newspaper here. Down at the ground, but everything at the ground is occurring by what's happening aloft here. So let's look at the jet stream. This is the jet stream here, and this is high and low pressure here.
I am going to show that atmospheric pressure is a complete hoax, and it's just another number that does not apply to the real world. Just like the assumed speed of light.
But I want to spend a few moments on the constants of nature too, because these are again assumed to be constant. Things like the gravitational constant, the speed of light, are called the fundamental constants. Are they really constant?
The assumed shape and size of the Earth.
Under the approximation that the Earth is a perfect sphere, we can relate the angle separating the pair to the total number of degrees in a circle, 360, to the ratio of the ground distance separating the pair and the total circumference of the Earth.
The assumed distance to the Sun.
Degrees, creating a triangle that looks like this. M represents the moon, E and S the Earth and Sun. Aristarchus had determined EM, the distance to the moon. If he could determine the angle E, he could solve this triangle and determine ES, the distance from the Earth to the Sun.
The assumed rate at which things fall.
2, 1. There you go. So I hope you predicted it correct. As you can see, they both hit the ground at the same time. 3, 2, 1. There you go. So I hope you predicted it correct. As you can see, they both hit the ground at the same time.
Okay, I want to do it in normal speed so you can appreciate how fast the feather actually falls. So here's feather in a vacuum, normal speed. 3, 2, 1.
See, they both hit the ground at the same time. Hit the ground at the same time.
And any other assumed constants are just that. All assume numbers with zero evidence to back up their assertions. And with zero evidence of these constants, you have to ask, how did they derive a constant pressure of 14.7 pounds per square inch of atmospheric pressure?
Now, why that is interesting to know is because the QNH obviously is different between different airports. So, for example, today, the QNH here in Girona is 1015 hectopascals. And I'm just about to start flying. We're going to fly to Baden-Baden in Germany. And the QNH there is going to be much lower. It's going to be 1002 hectopascals. Okay. So, it's really important that we use the correct pressure setting at the airport we're at, because otherwise our altimeters is not going to show us where we are. Okay. If I, for example, sit here, QNH 1015, and then I wait for a few hours and the pressure drops, well then the altimeter will assume that I have climbed during that time, and it will show me if it's dropped, for example, 3 hectopascals, well then it will show that I'm actually 90 feet higher than what I actually am. This is why it's so important that we continuously update the pressure setting when we are either departing from an airport or descending into an airport.
Once you understand how they arrived at this atmospheric pressure calculation, this will open a Pandora's box that even Alice would struggle to open. 14.7 psi of atmospheric pressure was derived from a 33 feet water pressure formula. At sea level, you start your dive from 1, and as you descend deeper underwater, the pressure and density increases and the volume decreases. This relationship between pressure, density and volume stays consistent as you dive. At 33 feet deep, you are at 2 atmospheres. 2 atmospheres underwater gives us a pressure reading of 14.7 psi. But atmospheric pressure at sea level is also 14.7 psi. How can this be, you may wonder? kPa, otherwise kilopascal, and psi, pounds per square inch, are both pressure units. 33 feet of water is 99 kilopascals, which equals to 14.7 psi. Confused? Well, get your thinking caps on. 33 feet deep underwater is the same pressure at sea level. Yes, you heard me right. If 0.33 feet 4 inches of water is 1 kPa, kilopascals, what do you suppose it is in psi? Four inches of water and pressure is 0.145. You remove the water and you remove the pressure. In a nutshell, 1 inch of water is only 0.036 psi. High altitude balloons do not burst due to an outside force pressing against the exterior of the rubbery surface, or because it lacks one. As the balloon rises, there is a constant force from the warm gas within the balloon pressing against it, and as it ascends, the rubber begins to freeze, in turn causing the balloon to become a lot weaker and a lot less stable, therefore making it easier for the warm gas to break open the balloon. You can clearly see the gas does not rapidly rush to fill the space or void. That's because there is no void to fill. The so-called pressure is the same no matter the height. The only thing that changes is the temperature. The molecules will move around freely in any direction until their temperature changes, which will cause them to either fall or rise. All they give us is lies, lies, lies. They give us data without demonstrations. They give us demonstrations with fraudulent explanations. So I have to ask, do you want a trick or the truth? Trick or truth? Trick or truth? I'm always in favor of the truth, so let's begin there. An honest approach for me would be to ask, where in nature do we even observe or feel or sense atmospheric pressure in the first place to ask such a question? But I am willing to beg the question in order to walk with anyone who thinks that there is an atmospheric pressure. Let's take a simple science experiment, for example. An experiment that will demonstrate atmospheric pressure. Sounds good to me. Let's do it. But lest I remind you, experiments are to show cause and the proclaimed effect. For example, let's say we observe liquid rising in a container or an egg being pushed into a bottle. We are told that these effects are due to atmospheric pressure. I would want to test this. How did this happen? What really caused the liquid to move up the chamber? My hypothesis would be along the lines of, well, I guess there is some type of force pushing or pulling the liquid, and my belief is that the flame has something to do with the effect. Time to start manipulating some variables and start removing my beliefs. Here is a variable that could be manipulated. This fire could be the cause and maybe has something to do with why the liquid reacted in the way it did. Let's remove the flame and see if we have a different result. Yep, just as I suspected, the liquid does not rise on its own. It needs a vacuum to suck or pull the liquid up. Just as we saw with the egg, it needs a vacuum to suck the egg in. Conclusion. Having removed what was hypothesized to be the cause of liquid rise is in fact the cause of liquid rise, which is the flame burnt up all of the oxygen in the chamber, creating a vacuum for pull or suction. Very simple science for determining cause and effect. Practical scientific experiments determine vacuums can only suck or pull, with zero applied pressure. This is a demonstrable fact, shown time and time again.
You won't be surprised to learn that fluid flowing in a pipe downstream of a valve also has momentum, and that fluid also has a hard time stopping without a big fluctuation in pressure. But unlike upstream, where the momentum is carrying the fluid toward the valve, on the downstream side, the fluid is trying to flow away from it, so the spike in pressure is negative. In other words, it creates a vacuum. You may have noticed something different about this pressure gauge. It only measures pressures that are below atmospheric. It's a vacuum gauge. Watch what happens when I slam this valve shut. We get a very strong vacuum in the pipe downstream of the valve. The momentum of the fluid in the water hose is pulling away from the valve. That fluid tension sharply lowers the pressure in the pipe. This trap bubble gives a pretty good indication of what's happening as well. This is pretty far from a laboratory setting, no offense to the backyard scientists, but I'm seeing a peak of more than 30 inches of mercury, or 100 kilopascals, below atmospheric pressure. That's a lot of vacuum. In fact, it's enough to pull dissolved gases out of solution with the water. Take a look at the spot just downstream of the valve when I slam it shut. A spontaneous cloud of fine bubbles forms as the vacuum pulls. This is dissolved gases coming out of solution with the water. When the pressure returns, the bubbles shrink, but they don't immediately go back into solution with the water, so you can still see a light haze, especially when I turn the valve back on. Very cool in this demonstration, but bad news if your pipe wasn't designed to withstand these types of pressures. Just like positive pressure spikes from water hammer, this phenomenon has caused numerous failures of pipe systems from implosions.
Internal body pressure is 14.7 psi, which would make sense if there were really an actual force pressing on you. But the problem is, your heart pumps blood through your body at an average 2.4 psi. If we do the math, we have up to 2.4 psi pressure pushing out of the body and 14.7 psi pushing in the opposite direction against our bodies. An elephant, for example, has a blood pressure of up to 3.5 psi, suggesting that butterflies also have an internal pressure of 14.7 psi. To put things into perspective, a butterfly should survive fine under 33 feet of water because it has an internal pressure of 14.7 psi. All we need now is an oxygen mask for butterflies and we are good to go. So, which organ creates this extra 12.3 psi? Did we evolve a magical organ that pumps out this extra 12.3 psi? Which brings me to the ear popping myth.
Time now for a second opinion from Dr. Zoe and Dr. Sarah. Welcome to you both. Let's get on with the calls. We've got Claire on the line. Good morning to you, Claire.
Good morning.
So 2 years ago, you were travelling in the car and your ears started to pop, and ever since then, you've had this reoccurring ear popping.
Yes, I thought it would go, like, being on a plane or something like that, but it never did. Whenever I breathe in or swallow, I just hear constant crackling and popping.
Hello, my name is Dr. Jack Shohet. I'm here to talk about why the ears continue to pop. The most common reason for popping in the ears is a dysfunction of the eustachian tube. The eustachian tube equalizes pressure behind your eardrum with the outside world. And when the eustachian tube is not working properly, you can get this popping sensation in the ear. Now, the eustachian tube has the same type of lining as that in your nose. Anything that affects your nose can affect your eustachian tubes. And the most common conditions that affect the nose and eustachian tubes are things like a cold, allergies, such as
We can see ear popping is due to blood pressure and other health conditions. Fact. Another fact is that all esoteric gas pressure formulas are calculated in an enclosed environment. We do not live inside a tanker or a container. Atmospheric particles are free to move around and do not bounce off any walls, roofs, or floors. All free-moving particles are absorbed by surfaces it touches, which is how we know things are hot or cold. Many examples of this from...
See if it's actually hot enough to fry this egg on the sidewalk here in Arizona. We're in Florence, it's about 117 degrees. Look at that, it is cooking. Oh my god. Doesn't mean too much.
Don't pull it.
No, that's all right.
As you ascend up into the atmosphere, the molecules become colder, slow down, and essentially become a solid. In order for the oxygen to be properly absorbed into your lungs, it needs to be brought up to your core temperature, which is around 37.7 degrees, before being exhaled. So the fact is, it is harder to breathe when it is cold. So wear a scarf over your nose and your mouth to prevent breathing in ice crystals.
RPMs are at 5,800. That's 78%, 83%. Oh, we're climbing through 17,000. 17,013, oh my gosh. That's high. Screenshot that and do a couple more finger checks. I really shouldn't be up here too much longer probably. 82%. So we're at 17,064. We're gonna call this quits for safety. One more reading off of the barometric altimeter guy here, this app. See what it says. 17,200 on this one. And this air app says 17,100. Gonna kill the motor and come on down.
Now, think about it. If any barometer which uses mercury as its measuring tool will freeze up at temperatures below 50 degrees Celsius, so how would you measure the pressure? No air, no pressure, nothing to press on. No pressure, no gravity, no gravity, no globe. Which brings me to my bigger question. Why do things fall?
Objects fall because of cold temperatures. Objects rise because of warm temperatures or hot temperatures. And this can be demonstrated.
If there were a portal through which you could see all of the invisible air currents, temperature gradients, and differences in pressure and composition of air, then this is what it would look like. The heat rising off your head. And you could see the cold air poured out of a cup of ice.
Well, thank you very much there, Chemo. How did you think it went? You've been seeing the people in the chat. What would you say? Is it more thumbs up or more thumbs down?
I'm not sure yet. I mean, we'll see the response, really, I suppose. I've just highlighted some of the points that I thought were crucial, and we'll just take it from there. So,
okay. Well,
yeah, thank you for letting me present.
No worries. No worries. A massive thank you as well to Channel Q for sending over her live stream to actually come and watch this presentation. So a big thank you for that. And Jose as well. Jose for pointing that out, because I think Channel Q stepped in to take over his show because he was having a day off, I believe. So, just going to put a quick video on, and when we come back, we'll be taking questions. So, sit tight, Chemo.
Well, before you do, I just wanted if you could do what people thought. So, like, one, if people thought there is still atmospheric pressure, still they're not convinced, or two, if the opposite, right, or something like that.
Well, in the meantime, one's for supporting Chemo, two's for not supporting Chemo. Let's have a bit of music.
Thank you.
We're up pretty high, our heads are almost in the clouds, and their feet are chained to the ground with their chains of misery. They've got a hold of me, they won't let go of me. Let go of me. They might have gravity on their side, but something's pulling us high.
Yes, yes, I'm here. Well, we're told there's an atmospheric pressure of 14.7. So obviously outside of us, there's a pressure of 14.7 psi. So obviously an internal pressure of 14.7 psi would have to equalize that. Otherwise, we would explode, right?
Okay.
Very difficult. Like they say to us, it's very difficult to climb mountains. So obviously, our internal pressure is pushing out. Yeah.
Okay, so we have a question. I'm not going to name the name of the person saying it, but ask him if it's 14.7 psi at 33 feet below sea level, or if that 14.7 is added to the 14.7 that's already down there.
So, I mean, what does that question mean? We have an actual pressure unit, a real world pressure unit. So when we inflate our tires to 30 psi, so half of that, 15 psi, at 33 feet is the same pressure. So a real measurement. And when you're supposedly standing on the surface, there's supposed to be the same pressure that you would feel at 33 feet under the water.
Okay, so we've got a couple of questions here. So, question for Spurs: denser fluids like water will not rise even if they are much hotter than the air above. Apologies if it's been mentioned before. I think you actually spoke about that actually in the presentation, but we have another question. If it is claimed that is the drop in temperature that is the explanation for ears popping, why do you not get the same effect if you go outdoors on a cold day?
Ear popping is not due to climbing a mountain. So this doesn't happen for everybody. If you're in good condition, good health, like pilots, for example, they are in good health and their ears do not pop every time they go in high altitudes. It's the rapid change in temperature and health conditions will cause ear popping. So it's just a myth, basically. It's not everybody experiences ear popping.
Okay, so from the Purple Harpoon, how does Spurs think a barometer is zeroed?
Well, this is the question. You see, we don't know how they're calibrated. You see, so let's say you take a barometer from the factory. So, how does it calibrate? Like, is it set at 14.7, and then you go up and it starts to reduce? Obviously, a real pressure gauge would have something pressing on it, and so obviously, if you went underwater, the water would be pressing on that sensor and giving you a pressure reading of how much pressure is being applied. Now, in the real world, like I showed with the phone, for example, is the atmosphere pressing on the phone? If they want to say there is mercury inside the phone, either way, it wouldn't work at high altitudes because water, metal, and water, mercury, and metals, they contract at high altitudes and they would freeze, and then you wouldn't be able to take a measurement anyway. So, yes.
Okay, so we have a question from Peter G. What is the difference between gauge and absolute pressure?
Gauge and absolute pressure. What does they mean by absolute pressure? I'm not sure what they mean by gauge and absolute pressure.
Well, that's the question. I'm not here to help you.
No, I mean, I asked them to elaborate what they mean by absolute pressure.
Okay, if there is an atmospheric pressure, why does Spurskimo think blood and tissue in our body would be compressed by the atmosphere?
Well, the same way is that when we go underwater, our bodies compress because there is a pressure. So I think people are confused about what pressure actually is. It's like an applied force. So you have all this water above you compressing and squeezing you. Now, when you're standing on the surface of the Earth, you don't feel anything squeezing you. So, if you were to climb a mountain and then climb back down, you wouldn't feel, something is pressing like you would underwater. So that's what I mean. Actual press.
Okay, so why does a PSI A gauge show 14.7 at sea level?
Sorry, say again. Why does
a PSI A gauge show 14.7 at sea level?
Because that's how they've been calibrated. Somebody's inputted this number. It's not like I said, it's not like you build the barometer, take it outside, or whether you're inside, it should immediately read 14.7. So somebody has to press in 14.7, and then, again, how do we know it's reading pressure? Or, a true way to know if it's reading pressure would be to go underwater. You would see it reading actual real world pressure, and then take it outside. But the problem is, it starts at 0, it goes underwater, it builds up to 14.7, you go back to the surface, it's 0. So who's calibrating this 14.7? And this is the point. This number, this is how I began the intro, is these numbers are just made up. Where do they get this 14.7 from in the first place? How do we know that we have an internal pressure of 14.7? So, it's like people asking questions about, well, how do we even have this number in the first place? Just like the speed of light, just like the rate things fall, demonstrated that these experiments prove the opposite, right?
Okay, so 2 questions in one. The first one's pretty much just a yes or a no. Does atmosphere have mass? And then following on from that, from right at the hand, can Spurs define temperature? So first question, does the atmosphere have mass? Yes or no?
It has mass in a container. You can't take measurements in the real world like that outside. So if you have a gauge, it will not press on the gauge unless it's wind, unless it's something with a force. But just strictly atmosphere, no, that won't happen.
And can you define pressure?
Pressure?
Temperature.
Yeah, temperature is just the degree or the intensity of heat of an object. So whether it just describes whether something is hot or cold, the temperature of that.
Okay, we have a question. So during the candle experiments that you showed in your presentation, isn't the oxygen that the fire needs being drawn out of the air what actually pulls the water up, or do you believe something else is happening?
So it eliminates the oxygen. But you can't burn in.
What do you mean? What do you mean it eliminates the oxygen?
So you can't light a candle with no oxygen. So if you tried to light that candle once the flame had gone out, you wouldn't be able to light it. Why? Because the oxygen has gone. So you've created a vacuum, an area where there is no oxygen, which creates a pull. So that's the mechanism we see here.
I think the question was more to do with you claimed it was the fire, and what he's saying is that the fire resulted in removal of the oxygen. So essentially, it could have been either or.
Well, we're looking at the cause of why the liquid was rising, and no flame, or basically. If you don't have the flame in this experiment, then the liquid won't rise. The egg won't go into to the bottle. So that we're looking for cause and effect. There's an effect here. Was it the atmosphere pushing the liquid down and up, or was there something else going on?
Okay, so a question from Gleam, who says, is Spurs aware The electrostatic gradient from Earth's surface correlates with air pressure, and they both become their minimum at 31 miles.
No, again, the idea of pressure means there's a force, and we know the ball earthers, the globe earthers have gravity as that force, which we know is not a force. So even in the globe earth paradigm, this is null and void for them, because without gravity there is no atmospheric pressure. Now, flat earthers say there is a pressure, a force, but they can't demonstrate or describe this force. So it's just hairy-fairy, without being so rude. But if that can be demonstrated, this force of this pressure, then I'm more than welcome to listen to that.
Okay, so Peter G is basically just saying that stepping out on a cold winter's day, you can get a drop of 50 degrees C. Still, he never gets that effect on his ears. But with increased elevation, perhaps.
Yeah, perhaps, maybe, it depends. I mean, again, it's a rapid change in temperature as you go up. Down here, it's always there's always a warm air. You've got your own internal temperature. Many factors. If again, he could be acclimatized to where he lives. So it's not like it was summer one day and then extremely cold. The next day you acclimatize. Just like when you climb a mountain, you're supposed to acclimatize, right? Why do you acclimatize? Because your body temperature needs to adjust to the outside temperature. And like I explained in the video, you're breathing in particles that are basically solids. So, yeah, that's why it doesn't happen when you just open your front door.
Okay, so a question from Zan, who asks, if you don't know the difference between absolute pressure and gauge pressure, why on earth you make a presentation about pressure? Does he go by his feeling for pressure?
No, we're going by demonstrations for pressure. So if he knows what he's talking about with this absolute pressure, then obviously he has to be able to demonstrate that, right? Because we are about demonstrations and not what we believe. And so I've been able to demonstrate that there is zero atmospheric pressure. So, coming up with terms and equations and, what I would call word salad is not going to prove, atmospheric pressure. Pressure requires a force. So the globe earthers can't prove the force. And, I don't know, flat earthers want to say there's atmospheric pressure, but obviously you need a force for that.
Okay, so question from Beyond Practical Examples, who says, question for Spurs, ears popping with increasing altitude is not a medical issue as you claim. Why did you lie about this?
Yeah, I mean, you'll have to watch the presentation again, where there was a lady who she called up to get a second opinion. She's just walking around and her ears are popping. She has an issue with something inside. She has health problems. She tried to go into an aeroplane. She thought it would stop, like equalize or something, of the myth that she'd been told. It didn't. So she went up. It didn't pop. Popped. It was all over the place. And then I showed another doctor afterwards who just explained if you have a cold, it's all to do with the sinuses, the nose, the nasal, the ears. It's all connected. And it's all down to health conditions. So it's just a myth that going up higher, your ears will pop. So not everybody's ears will pop.
Okay, so a follow-up from Gleam. The force of the electrostatic field is measured with a field mill. He can Google, and NASA even have a few.
So you see, and this is what I have to bring you back to. So now we have Gleam. I know I love you, brother. I know you are a flat earther, and now look what you're doing. You are relying on NASA, which is what we've been trying to avoid. You're going back to the same kind of argument that the globe earthers would bring. We rely on these people. They tell us. They do it. And this is what I'm trying to say. This is why I brought it forward, because are we going to be able to demonstrate this belief of atmospheric pressure? And we can stamp our feet, we can scream and shout, we can, get into all kinds of, arguments, but demonstrations, I feel, are the key. So if you're not able to demonstrate a pressure, absolute pressure, then it has to be your belief, right?
Okay, so we have a question from the Purple Harpoon. Made me giggle a little bit, actually. Would yourself be willing to enter a vacuum chamber to verify that zero pressure will be different to atmospheric pressure and video it?
We can't have zero pressure in a vacuum. Not even NASA are able to make a vacuum 100%. So if you can do that, then I'd like to see that. I think CERN would also be very interested if he could make a perfect vacuum.
Okay, so follow-ups from the Lumberjack, basically. Squids, whales, big squids, little squids, how come they don't get crushed when they go deeper under the water?
Yeah, I mean, this is the big question, right? I mean, there's sea life that can go way deeper than submarines. They can survive at very, very deep depths and things like that. Yeah, it just shows you that we don't actually know everything that we've been told. And another question is, we're told that high pressure means high temperature. So at the bottom of the ocean, there is a high pressure, all of that water, but the bottom of the ocean is supposed to be cold. So you have high pressure and low temperatures. So, that's something that people can think about, or a question they could ask: why is the bottom of the ocean cold with all that pressure?
Okay, so let's see. So from Chris Cruel, do you believe if a tree falls in a forest and no one can hear that tree fall, does it produce a sound?
Well, of course it makes a sound, but that's philosophical, isn't it? So it makes a sound, but you're just not there to hear it. That's not a phenomena or anything like that. That's obviously that would happen.
Okay, so from Right the Hand, if pressure is just a number gotten from a man-made object, isn't that what temperature is?
No, because you can feel temperature, and pressure is not a myth. You know what pressure is when you're in the bath and you're just lying there. Your head is out of the bath. You're just lying there, relaxing, thinking what you're thinking. You can feel the pressure of the water, just that slight, the water over your chest. You can feel that pressure, right? That's real world pressure. And obviously, as you go deeper under the water, there is more pressure. So, atmospheric pressure is not a real thing, because the atmosphere is not pushing on you or squeezing on you. What's actually happening is temperature is, well, I don't want to say pressing on you, are absorbing. That's how, we tan, because of the climate. That's how we cook food, because there's temperature, things like this. So things are absorbing this atmosphere. It's not pushing us, and for me, there is no pressure, and that cannot be demonstrated.
Okay, so question from B-Ball for Life. Spurs, why can't we breathe on the top of Mount Everest?
So, because we have a body temperature of 37.7 degrees, and the temperature up there is obviously a lot cooler. So the particles up there would make it a lot harder for you to inhale, and so when you exhale, there'd be a temperature differential. So you're basically breathing in ice particles when you're up there. So there is air, the air is still up there. There's no gradient of pressure there. The only gradient, if you want to like to call that, because even when you get to the highest heights, we don't know what the temperature is up there at the highest heights. Like, what is the temperature? So, but down here, with the weather system that we have, we can obviously take arbitrary temperature readings, but we can only measure temperature with sensors. So we know when it's hot and we know when it's cold. And we only know when there's real pressure when we go underwater, or there is a physical object on you, not atmosphere.
Okay, so we have a bit of a statement from Supercurve, who says pressure is experienced by a surface. Without the surface, the conditions for pressure still exist, in brackets, energy of gas molecules, etc. But we do have a question who's from Said and Doan. You said that the atmosphere has no mass. Does it have density?
Again, it's because of what we're learning more and more about the atmosphere. And I mean, you should know this as well, looking at your observations with the ships. I don't want to bring you in, but we're looking at the atmosphere like it's a tangible. I mean, we look at dust particles. Dust, when it settles, builds up. Yeah, we can see that. But if it's like a hot day, and you might call high pressure, this day is high pressure, it's high temperature. So when the sun is beating down, like I showed with the egg, is that egg being pushed down more? So, the hotter the day, are we saying we're being pushed more? There is more pressure. So we have to pump out more pressure in our bodies or something like this. So it doesn't make sense, the whole pressure argument for me. Temperature is what we feel. Temperature is what we know. And pressure is what we feel, like I said, when we go underwater, or an actual object is applied to us.
So, a question from right at the hand, which I can probably answer for you. Have you ever seen the tanker truck that pulled a vacuum in? Yes, it was in the presentation. So from Supercurve, can you ask why ears pop when increasing and decreasing in altitude? And along that's a different question. So yeah, what about that one? Can you ask why ears pop when increasing and decreasing altitude?
Yeah. I mean, they're going to have to watch the presentation again. I did go over that. I don't mind going over it again. This is a myth. This ear popping myth. It doesn't happen to everybody. And if you're in good health, if you're a pilot, for example, where you can train for this type of thing, where temperatures drop, your ears will not pop. So it depends on who you are and how you live, right? So it's nothing to do with that everybody goes up and they all experience ear popping at the same elevation for a start. So, for example, you take a family of 5 and they walk a mountain, everybody's ears should start popping at the same time, which is not what we see. Some people who are unhealthy might say, oh, I feel like my ears popping, and others might say, no, I'm fine, my ears are not popping. So it's different for everybody.
Okay, so from Crow XE, who again has done a presentation on this show before, ask if you are aware that an empty plastic bottle collapses as we descend. It's a fact that many people know to be real.
I'd have to see that demonstration. But again, it's a drop in temperature. It's a rapid drop in temperature. When we see, when this happens, like in a vacuum, for example, if you boil water in a vacuum, it boils. So if you have water in a vacuum, it boils, and then it eventually freezes. Now, this is a rapid change in temperature. Obviously, it's inside a container. It's a controlled environment. And if this is happening outside, this rapid change, so obviously inside the container, remember, the bottles, the crisp packets, they're containers. So that exchange of temperature is happening within that container, which we get to see in the vacuums, with the experiments of water in a vacuum.
Okay, so why do helium balloons pop with increased altitude?
Again, this is another myth. So what would happen is the balloon would rise, so you have warm gas inside the balloon, and the balloon is rising and the outside temperature is dropping rapidly, and this warm gas wants to escape, is pressing inside the controlled environment, so the exterior of the balloon will rapidly cool down in temperature, right? This is clear. It's like almost going into a freezer of some sort. So obviously, as we know, the exterior is weak, and all we see happening is the gas is pushing on a weak wall, and that's the reason why they burst. So obviously, you get some people breaking the world record because they have stronger materials. The stronger the material, the higher you could go. And this brings me to why rockets, I just need to get this in as well, why rockets don't work in space. Yes, it's not just that there's nothing to push off, but they cannot keep the temperature of the rocket, the exterior of the rocket, warm enough, because everything is just freezing up. So when they try to light, just the same as so it's not a vacuum, but it's like a vacuum. It's just very, very difficult to burn anything. All the material. This is why they talk about. It makes a lot of sense now when you hear that, like those NASA engineers speak about. We need to find the right type of shielding, the exterior, to withstand the radiation. But now, temperature is understood. They need to prevent the exterior from, freezing up and breaking up, basically, because that's what would happen.
Okay, so again, another question, but this time from Blue Marble Science, who asks us the same question you didn't quite answer properly before, but what is the difference in gauge pressure and absolute pressure? If you honestly listen, if you don't know, honestly, I would rather you say you don't know and you'll look into it in the future. Just don't make something up, because if you make something up and it's wrong, they'll always come back to it and say and they'll pick it out. So if you just don't know, say you just don't know. It's fair.
He's asking about a perfect vacuum, and we don't have a perfect vacuum. So I don't see how this question is relevant. So he would have to be able to demonstrate absolute pressure in this matter.
Okay, so how do atmospheric altimeters work, and why are they accurate?
They're not. Again, in the video, I went over this. The pilot was telling us that he has to constantly calibrate and update the system because, because of the temperature changes, the rapid temperature changes. The altimeter can think that they're higher when they're not. They can think that when they're even on the ground, that they're like 50,000 feet in the air or something, so they have to change it. He was talking about he's just sitting there on the ground and the pressure drops. Well, how can the pressure of 14.7 psi, he's sitting there and the pressure just drop? To 10 psi? I mean, how on earth would that work? Did the guy who's pumping the air into this imaginary container, it doesn't make any sense whatsoever. So the altimeters, they malfunction because of the temperature, because obviously as they go higher, temperature changes affects their instruments. So yeah, they're not reliable, and they would need demonstrating again.
Okay, so do you know how insulation works?
Insulation, is it relevant? Is it in terms of what?
That's just the question. Again, I'm not here to help you. You've got to decipher what they mean with that.
The guy who's asking in terms of what? Yeah, keeping things warm. I mean, it has to be more. It has to be more. Be a bit more elaborate.
Okay, so Chris Barker asks, earlier you said that airline pilots' ears don't pop. Can you ask Chemo to provide that data to support the claim?
Yeah, absolutely. Again, in the presentation that I played, that pilot talks about ear popping. Again, I didn't want to put too much into. Didn't want to make the presentation too long, so I could have included that. But I did include a few doctors who have spoke about just a medical, it's health conditions. But nonetheless, yeah, I could provide that. I mean, how does he want it?
we could listen to it, of course. But
Okay, right. So from Joe Mama, do you believe that a weight scale would register a different weight of an object at the poles versus the equator, at altitude versus sea level?
At the poles?
Versus, the poles versus the equator.
Well, this is... So, we're begging the question here. So, we're imagining there's a ball, and we're imagining there's poles, and we're imagining there's an equator. How would it work on the globe? So, the pressure would be... what would it be? It would be less pressure at less elevation.
Okay.
No, higher elevation is less pressure. Yeah, so that's the same as there on a mountain. Less pressure. Yeah, so the equator, if it's wider. Yeah, so it's the same thing.
Okay, so a question to me from Tamson Ben. Ranty, how can you keep a straight face watching and asking questions and listening to his answers? Poker face. Poker. I used to be quite good at that, so bit of a poker face there. So, from the Purple Harpoon, does Spurs think he could be wrong by any chance?
Absolutely. This is why I've made the presentation. If anybody is able to demonstrate atmospheric pressure. Now remember, people just, they talk a good game, right? And they say a lot of things like, we have, they have, we've done. Now, I've been able to show the we and the they, where the gravitational, the rate that things fall, do not fall at the same rate. I've been able to show that atmospheric pressure, the so-called atmospheric pressure, doesn't exist. So, as far as I can see, the demonstrations speak for themselves. So it's not a case of whether I'm wrong. It's maybe I've interpreted the demonstrations wrong. Maybe I've overlooked something. But yeah, I would be willing and definitely, good to see someone demonstrate atmospheric pressure. We're talking pressure here. Like, as if you go into water, you feel that pressure. We want to see that same pressure, not like when you take a crisp packet, oh look, it's expanding or something like that. We want to see an applied pressure, and then we want to measure that pressure. That's what we'd like to see.
Okay, a yes or no answer. Are pressure and temperature related?
It's not a yes or no answer. In a container, this is related. Yes. So you can only have like a vacuum in a enclosed system in a container, and you can only have gas pressure in an enclosed system. So yes, this is linked, pressure and temperature. But outside, in the real world, there's no pressure, zero pressure whatsoever. But there is temperature because you feel it, right? You know when it's cold, you know when it's warm. But when it comes to pressure, the only time you feel real world pressure is underwater, or like I say, when there's an object on you in the real world. So yeah.
Okay, you say there is no mass and no density and therefore no pressure in the atmosphere. Can you give an example to demonstrate how weather systems work?
How weather systems work? Again, this is the temperature exchange. So you have warm temperatures, cool temperatures, they're interchanged. So obviously the main thing is it's all to do with the sun and the moon and the temperature that they give off. So that affects the atmosphere. And so there's no pushing or there's no force. So unless you're going to suppose the sun is the force, because that's where the temperature comes from. If there is no sun, the temperature is very low, and if there's sun, obviously, then it's high. So it's nothing to do with any type of pressure outside in the real world. There's no pushing or pressing of any kind in the real world.
Okay, so Saucy London wants to know, do you think this is going to be one of the housekeeping questions? And we have a statement from Crow XE who says, he used to be on a helicopter many times, no significant change in temperature, yet bottles collapsed every time we descend. I call everyone to try it, even on an elevator.
Yeah. Yeah, I mean, everyone has to try it. Yeah, I mean, remember, inside that bottle, there is the temperature. So you would have to, there's a lot of details now that people have to know. So what is the temperature inside of the container versus the temperature outside of the container? And remember that they have to equalize. The temperature inside the container is always trying to equalize with the temperature outside of the container. It's the same way that with people, while you sweat, right? If you're too hot on the inside, the temperature's too high. This is a lot of pressure, you might say. But, you know, this is temperature, so you're sweating and it's pushing up. So there's a rapid temperature change going on here. And the same way is with bottles or any kind of crisp packets or any container. If it's inside an enclosed environment, there will be real pressure. There's a real force. So in a container, so I think people are confused. Like, if we have a container, there is real pressure, but we don't live inside a container. In order for there to be atmospheric pressure, the particles have to bounce off a wall. So let's think about it. We have a balloon, right? And that balloon goes up into the atmosphere and it bursts. Now those particles from that balloon will do what? What will happen to those particles? Now they will start to fall, obviously because they're not warm enough or not hot enough. If they're hot, they'll rise. You know, if warm things rise. So they'll start to fall, those particles. Now, let's say we could take a microscope into the microscopic world and follow those particles. What will happen to them? They will start to descend. They will go down, down, down. Now, again, depending on the temperature, will affect them. But let's just remove that for a second. Let's say it's not temperature and they're just... Because you guys want to act like they're a solid. So they're falling down, and they disperse, and let's say they hit humans, animals, plants, houses, whatever, the ground. Do you think those particles are going to bounce off those objects or be absorbed into those objects? Now, if you're saying that they're bouncing off them, again, you have to demonstrate this. Then they're not dust. Dust will settle. The atmosphere is not dust. So dust will, land on your face or land on, on top of the unit or whatever, the television or something like this. And that's what we can see. We can see that pressure, if you could even read that pressure. But yeah, that will settle onto an object. But in terms of the atmosphere, there are many ways of understanding this. When it rains, you feel the pressure of the rain. That's the real world pressure. The particles around the rain, where it's not raining, through that rain, if you can imagine that, you don't feel that. You don't sense that. You can't measure that. You could only measure the water, real world pressure.
Okay, so a couple of mini statements / digs. Here we go. One from Brian Leake, who says, Spurs, how can you have such a great argument and then crush it by using temperatures, with lots of exclamation marks and question marks after that? And then from Paulster X, who says, DFOTY, for you, apparently, that you might even pip Anthony for the title this year. The old trolls in the chat. But from Chocky, okay, if Spurs believes something taking a measurement is just a man-made device that we can't trust, how can we measure atmospheric pressure? Will he trust that?
I've just said this. How are they going? Because we know how. Look, let me. There's nothing magical or mystical about this. We know how to measure something when there is pressure applied. So if we have a scale, for example, so we know there is a pressure being applied to the scale and it's given us a reading. If you go underwater, you can feel the water pressing on you all around you. This is a real world pressure. Now, when you come out of the water, there's water still on you. You don't really feel that pressure, but you know there's water still on you. You get rid of that water, the pressure has gone. Now, we're being told there is another pressure, but again, it needs demonstrated. There's no force to show that pressure. And, you know, again, it's understandable because the globe earthers have gravity. That's their force. Like, if you pushed a car, you would be the force of the car moving. So, in their world, they have a force, which is gravity, and then the atmosphere is being pushed down as a result of that. But flat earthers, we don't have gravity. Or do you? We don't. So there's no magical imaginary force, do we? So how are we going to explain atmospheric pressure with no force? This is going back to the pseudo science understanding of trying to figure out, you know, what's happening here. So yeah, we have to go back to demonstrations, and if there is a pressure, we have to demonstrate it in the same way that we know there are other pressures. Exactly the same way.
Okay, so Super Dave wants to know, can you ask to what level Spurs has formally studied science? He talks like a professor, but he has a child's understanding of the subject.
Well, look, I have an understanding by I've been obviously researching this topic, but it's not about me per se. It's about the information. Does the information hold up? Does the information stand up to scrutiny? And I think, you know, what I've done, anyone can do, whether you are a professor, whether you are a student, you can actually demonstrate whether there is an actual pressure. And I think that's the most important thing, is to focus on the experiment itself and the question at hand, right?
Okay, well, speaking of experiments/tests, Just Legend wants to know, can Spurs explain what tests he has done to confirm his opinion on the inner ear, and why doctors and data disagrees with his opinion?
What tests have I done to prove, what, in terms of climbing a mountain or something? No, I haven't climbed any mountains. I've been in planes. Sometimes the ears want to pop, sometimes they don't pop, sometimes they do pop, but it doesn't happen to everybody. So I've been with an entourage, and not everybody ears pops at the same time. So it's just a myth. It's an old wives' tale. It's part of the globe myth. Yes, it does happen, ear popping, but again, it's down to health conditions.
If we can measure pressure, how are we wrong about having measured atmospheric pressure?
Because atmospheric pressure was never measured in the first place. This was part of the globe deception. Because remember, I'm addressing the flat earthers from a globe earther question, but the atmospheric pressure was only given to us because of gravity. So they said, well, why aren't the particles just going off into space or whatever? Oh, because of gravity. Oh, do we live in a container? Is it a container? Is there gravity? So there's been a lot of discussion about where do we live. But, what happens is the particles, the atmosphere, they go up, they cool down rapidly, they freeze, they fall back down. Then the atmosphere will warm them back up. They go up and down, up and down. So it's a lot to do with the sun, like I said. The sun plays a huge role in what the atmosphere does and doesn't do, but it doesn't apply pressure. It's not like a hairdryer or a blower, a heater, when it's a hot day and pressure of heat is not blowing at your face. You don't say, oh, look, something is blowing, or this heat is blowing this pressure at me. You just say, oh, I feel the heat. The heat is being absorbed into me. This is great. And you move forward into this. You're not resisting this. You don't move backwards. You step forward into this layer of temperature. right? This layer of heat, and not pressure. If it was a pressure, as it got hotter, you would step backwards, right? And you close your eyes because it's too bright. You don't close your eyes because there's a huge pressure on your eyes, like being pushed on your eyeballs and causing you to close your eyes, right? It's just too bright. And then you step forward and you bathe, you bask in the temperature, in the atmosphere. And yeah, that's what it's down to. So there is no any kind of pressure whatsoever. And again, if somebody kind of believes that there is, well, it needs demonstrated.
Okay, so following on, essentially Druss is saying, so no actual tests then to form your opinion. But we have had a super chat from Beer Can Girth who says, in 500-mile radius of me on the ground, there's never more than 1 pound difference in PSI. However, go up to just 20 miles in elevation anywhere, the difference is over 10 pound always. Why?
Again, how I'd have to ask. This is very key. People are just throwing PSI. Like, in order for this to happen, those particles have to be bouncing off the floor. So it's like he's standing over the floor with his device. There are particles that are hitting the floor, bouncing up, and he's reading that. Or they're bouncing. It's like, is he saying he's reading? His device is reading particles that are going up, hitting the roof, coming down, and he's reading those particles. Or are they going across to hit the wall? You know, this is something that I truly cannot visualize because there's no container. In a container, you could do all of these things. You could say, look, you know, you would add pressure, you would apply more particles, and then you could say, you know, this is how many pounds per square inch we can read. But outside, there's no container for him to make a reading in the first place. So again, when people are describing pressure outside, you have to come with a demonstration and say, look, here is my reading of the pressure. How do you explain this? Yes?
Okay, so we have a question. How do barometers work if there is no pressure? And how was and question, the barometer was invented in 1643 before the concept of gravity. How was this observation connected to gravity?
Quite right. So in 1643, as you just said, a student of Galileo named Tory, Ivan Torricelli. I don't know if I pronounced that right, but he invented the Chalian barometer. So what he did, he took a glass tube and he filled it with mercury, and you know he kind of turned it upside down, and he stuck the open end into an open dish of mercury. And so he looked at the mercury in the tube, and he saw that the mercury was 760 millimeters high at sea level. So what they did after this, they took calculations and said, well, you know, they assumed that if they were to go up a mountain, the liquid would reduce in size, would go down, and the column would be around 520 millimeters. But what they didn't realize back then, because obviously this is ancient knowledge, this is the old world, is that the mercury expands and contracts in temperature. So obviously, if it gets cold, when you take that device to the top of a mountain, they freeze, the particles freeze, they contract, they get smaller. Now, if they get smaller and make more space in the tube, that means they're going to fall. They're going to go down the sides. They're going to be more space in the tube, and they're going to fall down, and that's the reason why it drops. So obviously, as they expand, as you bring it back down, it expands like a balloon, so it would push itself up because it's trying to fill the space. See? So nothing to do with pressure, everything to do with temperature. And this observation or this experiment could not be done without temperature in the first place. So even in a container of any of that kind. So yes, The device the barometer is fully understood, how it was invented, why it was invented, and where it was used, and it was basically based on presuppositions from Galileo.
Okay, so I'm going to ask this question because it's been asked a few times. If altimeters are so unreliable, why do skydivers rely on them when their life is at stake?
Well, I mean, what do they mean precisely? I mean, they have to elaborate again because,
We're obviously talking about a skydiver here, so they have an altimeter to tell them how high they are when they've jumped out of the plane. Yeah. So they need to know the altitude, and especially at night. At night,
yeah.
So the life is at stake. Essentially, they need to know when to actually pull the chute. So right. I would assume that would be the makeup of that question.
Yeah, but this is height, not pressure or temperature. So this is a height question, yeah?
It's about an altimeter. Altimeter.
Which tells you how high you are, yeah? Not the temperature up there. So I think he's got a bit mixed up. We're talking about pressure reading. So that, for example, the guy who jumps out of the aeroplane, does he feel less pressure when he jumps out of the aeroplane or less temperature? And I would say less temperature. Well, depending on how high he goes, yeah, for sure. But he's not going to feel less pressure. He's just going to feel colder until he returns to Earth. Absolutely.
So, Sleeping Warrior wants to know from you, he wants a concise one-liner for exactly what it is that you are claiming.
The atmospheric pressure is non-existent. There is no pressure gradient. There is this
a concise one-liner. Have a think.
Yeah.
Have a think.
All right. No. There is zero pressure. Atmospheric pressure. There is no atmospheric pressure. Yeah.
Which one is it?
And if you think
we need a quote. We need a quote here. We need a quote from you. Come on. We need a concise one-liner.
Yeah. Well, I've said atmospheric pressure is non-existent.
Okay. Right, let's see if there's any more questions. Any more questions? Hang on, wait a second. Okay, so from Just the Legend, you claimed the discovery barometer was necessitated by Newton's observation, not the question he answered.
I didn't say Newton, I said Galileo. He was a student of Galileo, Tory.
Okay, so from Peter G, why do Mercury barometer work and shown change with altitude, even in temperature-controlled environment? So both observation is at the same temperature.
Yeah, they only work in a controlled environment. If you take this device to high altitudes, the mercury will freeze, become a solid, and will not make any readings. And obviously, if you control the temperature, I mean, this is very simple, isn't it? So if you control the temperature of that barometer, well, then you're not taking an accurate reading, are you? That's the point. How can you control the outside temperature? You can't.
Okay, so again from Sleeping Warrior, who wants Asper's, if pressure equals mass over volume, the only way he could be right is if there is a mass or a volume issue, or there must be pressure, question mark.
Well, there's definitely a pressure question. Again, there's a confusion between the density layers. So I'm not sure if he wants the layers to be a thing, the density gradient, the gradient here, because we've been describing the gradient for a while now. So it's not that there's a gradient, it's a temperature gradient. But because obviously it's, you've heard Nathan talk about it's a dynamic system, and things like that. So that's basically what it is. It's a system that's very dynamic. It's not as cut and dry as what we've been told. So, but we know that obviously the higher you go, your instruments will not work because the temperatures are way too cold. So it'd be very difficult for you to control, because like I say, you can't control the outside temperatures, only the temperatures of your device in a container.
Okay, so we have a statement from B-Ball for Life. The pressure temperature law. This law states that the pressure of a given amount of gas held at a constant volume is directly proportional to the Kelvin temperature. And Al-K wants to know if you know the difference between a barometer and a thermometer.
Yeah. Both of those are trying to take readings of either atmospheric temperatures or pressures. They're both similar, actually. The barometer, like a home barometer, has a vacuum inside it at the top of it some way, and a thermometer reads temperature, obviously, again. What was the first question there?
It was more of a statement. Let me just find it again. Making me do some more work here.
Now, I mean, the main thing is that I'm learning about this, as well. It's not like I have all of the answers, but it's just from what I have an understanding of, at present. So I could be wrong. I mean, it's not like, I know everything, I have the answers. I'm not saying that. It's a case of me putting this forward and, seeing what the response is. So, if people respond with, "Oh, you're wrong," and you don't know what you're talking about, well, that's fine if that comes with a demonstration. Otherwise, we're just going around the same arguments as what we've been through with the ball earthers in the first place. That there is a force, there is pressure. You just don't believe it. You just deny it. It's not about deny. I mean, if my presentation consisted of demonstrations, so I was showing cause and effect. So we were told there was a particular effect and a particular cause, and we were able to manipulate variables and find out what the cause of this effect was. Now, so I can see that people are frustrated and they're probably, maybe angry and saying, "Well, you just don't understand. There is." Well, that's why I've done this, and that's what I want. I want people to kind of respond and show me with demonstrations actually where I'm wrong.
Okay, so Blue Marble Science wants to know if you know what the freezing point of Mercury is. If you don't know, don't guess it.
Well, again, I'm sure below 50 degrees you're not going to have Mercury doing anything other than being frozen. Minus 50 degrees Celsius, yeah.
Okay. Again, B-Ball for Life. Gay-Lussac's law. The pressure temperature law. This law states that the pressure of a given amount of gas held at a constant volume is directly proportional to the Kelvin temperature.
He's talking about in a container. All esoteric gas formulas are calculated in a container. So anything that he's describing to me is not outside in the real world. Somebody somewhere in a factory, in a laboratory, have taken a container and they've came up with the calculation formulas that they have. Now, he cannot show me this or demonstrate in the real world out here in the atmosphere where there's supposed to be this pressure. That's what we need to see. I can't answer a question if it's something that's happened already in a container. You see?
Okay, so Tusk wants to ask you, would you be willing to listen when you're wrong? And why don't you listen when you're told you're wrong?
Well, again, listening is one thing. We all can speak, we all have lots of words, lots of things to say, we all want to be heard and all those types of things. Very nice and well, good. But for me, the demonstrations speak for themselves. So once you demonstrate something, you can't deny the demonstration. So, I mean, again, for example, I've shown that in a vacuum, things do not fall at the same rate. Now, they might say, well, yes, they do. But if I've demonstrated this and I've shown that this doesn't happen, then who is he arguing with? Is he arguing with me or the demonstration? So, again, of course I would listen, but I don't really want to be preached to. You know, this is not a sermon where, you know, I have to listen or accept your word because you say so. The demonstrations speak for themselves, granted, and that's the key. So, yeah, I'll accept that I'm wrong if you can demonstrate this.
Okie dokie. Right, I think most of the questions have burnt themselves out. I think they've probably asked you like close to 30. You've answered at least 30, I would say. So yeah, I mean, you've not backed down from a question, even though I gave you the opportunity to say if you didn't know, don't take a guess. Apparently the answer to the question, well, it's hard to know exactly what the answer is. Somebody says minus 38 and somebody says minus 33.38. So I don't know which one is correct. You know, it's not something that I'm particularly up on, to be honest.
So if that happens, but this is what, if that happens, if at minus 38, you know, 40, 50, whatever, how are they going to take a reading of pressure? You know, this is key here. I don't think people are getting their heads around this. If there's no device to read pressure, and they're saying, so are they saying now at this point there is zero pressure? Well, again, they can't demonstrate that. You know, and if there's, you know, so many questions come out of this, and I hope it gets people thinking, asking more questions. The globe earthers, you have gravity, you have your get out of, you know, reality card, right? But for flat earthers, if there is pressure, you're going to be saying there is pressure, but you're not going to be able to demonstrate your claim. So it's going to be very difficult for you if you maintain this pressure argument. So I hope I helped, but again, if I'm wrong, it'd be a pleasure to see so.
We have another question from Sleeping Warrior. Asks Spurs if he agrees that we must be contained in some way to have a gas pressure that gives us a fixed volume. Gases do have mass/weight. If pressure equals mass over volume, we must have it.
No, so the container, it's not like a container, so it's going to be very difficult to describe because I don't want to say the vacuum of space or anything like that because we don't know what's up there. All we know is that very low temperatures happen at very high altitudes. So, you know, the idea that there is a pressure gradient that it gets, there's more and more mass of what exactly? Atmosphere. How is he defining atmosphere in these terms? Like, what are the particles? Is he talking about the water particles, the gases? You know, so this conversation needs a lot of discussion because it's so many details that need exploring. So again, the container, it doesn't need a container. It just needs the particles to cool down, freeze, and fall. But then you'd have to be able to find a way of measuring that falling, invisible, you know, stuff that you believe has a weight. That outside of the container you can weigh it and measure it. So I hear what you're saying, but there's no container. We don't live in a tanker or anything like that. So the particles are not bouncing. When they go up, they don't bounce. They would need to bounce for there to be a force. So that doesn't happen. They just go up, they cool down, and then they fall back down. And then those particles, when they get caught in the warm temperatures, they go back up. So you've got like you know, back and forth, up and down, like a system, a dynamic system. So it doesn't require a container. And if, for example, you did actually measure a pressure unit, well then yeah, we could ask the question. There must be a container, but you haven't measured. You haven't shown, Anthony. There is a pressure, like underwater. When you go underwater, you can say, look, the water's squeezing my hand, it's squeezing my device, there is actual pressure. So you really are begging the question, saying that there must be a container, there must be a container. And if there's a container, then there has to be pressure. And that pressure has to be red. And that's the only way we can get around this. So, you know, it is really begging, you know, we're saying, come on, there must be some type of barrier that these molecules are bouncing off. Well,
okay, so Jose wants to know if you're answering for all flat earthers or just yourself. So pretty easy question. What would you say? All flat earthers or just yourself?
This is just me. Yeah, this is my idea. Because this is to the flat earthers mainly, because the ball earthers, you know, the globe earthers, they have gravity. So we know gravity is nonsense. There is no force of gravity. So if there's no, like, again, if you're a ball earther, you have to have gravity for this pressure. But for flat earther, you know, like Anthony here, he will have to explain. Who's he going to explain to? What force? You know, he's been saying for the longest time, you know, George Munzer, that there's no force. So if there's no force, how can there be a pressure? So now he's saying container. But what's this container made out of? I can't even begin to imagine what it's made out of. So even if you were to say, I mean, we'll have to talk about this behind the scenes, but what it's made out of, because it would just sound bizarre. Yeah.
Well, Blue Marble Science wants to ask about the container. Here we go. So, Spurs, if it's a sealed, please ask Spurs if a sealed container is required for gas pressure.
A container.
A sealed container.
Sealed, not sealed. No. A container. So like a bowl or a cup or a fish tank. It doesn't have to be sealed, but it has to be contained.
Okay, so from Brian Leake, is it possible that pressure at ground zero is to equilibrium?
Is to equilibrium. So zero, yeah, there is zero pressure at ground zero, if that's what he means. So as you go up, the pressure doesn't drop, the temperature drops. So again, you have to elaborate, because again, a lot of these people have an impression of what this pressure is. So they're coming at this from a particular angle of not really understanding that how they came about the numbers that they came from in the first place. So, you know, I think a lot of people missed the presentation at the beginning.
Okay, so Ali B says, shout out to us too. Big thumbs up there.
Shout out Ali B. Thank you for watching, Ali B.
Yep. Charlie wants to know if you think that all barometers have mercury in them.
As far as I know. If something else is used, I would like to see. I'd like to know how it's used, how it's manufactured, how it's taken its reading, how the numbers are calculated. So as far as I know, yes, mercury is the standard way of taking pressure readings in the atmosphere, yes.
Okie dokie. Well, thanks for coming on, I have to say.
Wonderful.
You answered a ton of questions there. I'm not sure we're going to get anything else. You know, and if there is, they can always leave them in the comments after the video's uploaded. But Friday we have Soul Gear coming on Friday 9 PM, and we have another guest coming on at 6 PM. Dottie's World. I think it's called Dottie's. Called Dottie's World. Yeah. So we'll have two presentations on Friday, 6 PM BST. And 9 PM BST, and then hopefully, providing we can get a hold of Brenda, at some point next week we will probably be having a debate between Brenda and Right the Hand. So I already know that Brenda said she was happy to debate Right the Hand, but we just need confirmation of that and sort a day out. So finally get into some debates, which is what I wanted to get to in the end. Now then. Thanks for the presentation. If anybody wants to do a rebuttal video to this, get in touch, ranty@rantyflatearther.com. Put a presentation together, show your own proofs of how pressure is measured, etc. like that. And then hopefully at some point we could perhaps get into a debate. If you're up for a debate there, Spurskimo?
Absolutely. I mean, again, this is one of the reasons why I've done it, not just to preach. The key for me is demonstrations. So I think I've done that. So hopefully, you know, we don't just get a rebuttal of, you know, paperwork, nice words, and we actually see something physical and practical. That's what I'd like to see. So that person will be under pressure. So we'll see what happens. Yeah.
Under pressure. Well, you know for a fact with all the videos that we've had in on this presentation, etc., that, you know, this is instantly going to get demonetized, which is fine. You know, all my videos got instantly demonetized, and I've got to wait to 1,000 views before I can appeal it, and I've no idea why they instantly get demonetized. It's like as soon as they finish uploading, I must have a target on my back here, but with a bit of luck, we might get to 1,000 views pretty quick on this, because we've had quite a lot of people in. So we've had over 200 regularly. So thank you very much, everybody, for stopping by. I look forward to seeing you all on Friday 6 p.m. BST, and Friday at 9 p.m. BST. So if you want to stick yourself on mute, we'll do the round out, and I'll see you all in the next one.